All right, we're starting on page 466. We're working on line of best fit. So we're going to be going through activity 1, 2, and 3, skipping some parts, but for the most part, this beginning part is just kind of like an introduction or a worked example. So with this, it says a line of best fit is a line that is as close to as many points as possible, but doesn't have to go through all the points. When you display the data with scatter plot, constructing a line of best fit can help predict values not displayed on the plot. Either it's off the graph or maybe in between points. So the steps of how to create a line of best fit. For me, a line of best fit is not just connecting all the points. That's not even a straight line though. So a line of best fit is drawing a line that fits the trend of the data. So with this scatter plot, it's trending upward, and a line that goes through like maybe in between these points. So something like this. It could go through some points, like as you can see here. But if you're not sure how to draw a line, the best way to do this is first by plotting all the data. So these 5 points here. Moving on to the next page. After you have all the points graphed, you can draw a circle that encloses all the data. So here we have this like diagonal stretched out circle or ellipse. And then with that, you draw a line that kind of cuts that circle in half. So this line here, this is the thing that we want. Okay. Now, I want you to understand that when we're working within this topic, there is no one singular answer. We're looking for things that might be close. Like this, I think, is a good line of best fit. But like maybe someone drew this line. It's slightly different, but I think for the most part, it cuts that circle in half. Half the points are above and half the points are below, roughly. But just be mindful of that. So what we do here is we're going to be writing the equation of this line that we create. Okay. So step 4, determine the equation of the line of best fit. So what you have to do is you have to pick 2 points that are on that line. So here we do have 1 point that's right here. And it doesn't have to be any of these other points. Like it could be like this is a point that you can pick on the line. Or this right here on the y-axis. So what we did choose is we chose this point, 0, 1/2, and we chose this point, which is, what is that? It's got to be like 12, 4. Okay. Well, they chose this other one. So we have 2 points. And in order to write the equation, we have to find, first of all, the slope. So when we plug this into the slope formula, right, if you forgot, it's m equal to y2 minus y1 over x2 minus x1. All right, so that's what they did here. They plugged into the algorithm, they subtracted, they got this divided by this. And we're going to be using calculators for this. If you simplify it, you'll get this number as your slope. And then separately, to find the y-intercept, right, the y-intercept or b, that's where the line crosses the y-axis. So they found that it's a half because, that's where the line crosses the y-axis. It's about half on the y-axis. Okay, so we have here the x-axis as chain length of students, and the y-axis is time. This was, for us, we passed the book, so like we'll interpret that soon. But that's the equation, right? We plugged in a half or 0.3 for our slope and 1/2 for our y-intercept. And we know that our slope means that's how much we move, and our y-intercept is where we begin. So for this problem, it is possible to choose 2 different points and estimate those ordered pairs in a slightly different way. If we pick 2 other points, determining the line of fit may lead to different equations depending upon the estimated ordered pairs chosen to construct the line. However, when the data closely fit a line, the slopes of the different lines of best fit should be close together. So something roughly equal, and that's why we put approximately equal to instead of equal to. Okay, identify the slope of the line of fit and what it represents in the situation. So it is 0.3. I'll put m equal to 0.3 or approximately equal to maybe. The slope represents, since this is how much we move, this represents the change in mean time for each additional student in the chain. So we're going to say 0.3 additional seconds in the chain. This context talks about like squeezing a wrist, but for us it was just passing a book. So that's what it means. Every additional person that we add is a third of a second, roughly. And identify the y-intercept, right? That was b equal to 0.3. So what this means is the y-intercept represents the mean time in seconds for the chain length of 0 seconds. So this is where we begin. So we begin with 0.5 seconds to start. So maybe that was 0.5 seconds to, right, grab the book and pass it. But that there is some type, it's very close to 0.3, but that's where we begin. Okay. Now we use these equations to predict values. All right, that's another purpose of math, is to use the information that we have to predict values for unknowns or in the future. So what we have here are two key vocabulary terms. When you predict values that fall within the plotted areas, that is called interpolating. So what I mean by this, we have data for 5 students, for looks like 12 students, but we don't have here for 8 students. We can make a prediction. How long it'll take them to pass a book or squeeze a wrist, that's 3 seconds. Okay, so that's interpolating. When you predict values that fall outside of the plotted areas, that is extrapolating. So outside of the data values, we have, at most we have like around 30, but let's say we had like 40 students. We can make a prediction, I think this line probably goes here, of like how long it would take, and then we can make an estimate, maybe that's like 12 seconds for 40 students. Okay. All right. But we're going to make the prediction with varying values. So number 3, if you have already predicted the mean time for a chain length of 25 students, let's compare the prediction with the prediction using the equation of the line. And we'll be using an equation or a calculator for this. Is predicting the mean time for a chain length of 25 students an interpolation or extrapolation? So since we do have this, which is 30 students, and we have this, which is 22 students, 25 is somewhere right here. That is in between 2 known values. So that is interpolation. Right, because that is between 2 known values. All right, so I used the graph there, but we could also use the equation. All right, so let's go on to the next page where we're going to be using the equation. It says use the equation for the worked example to predict the mean time to complete a chain of 25 students. So 25 students, this is x. So we're going to have y equal to 0.3. Instead of x, we'll have 25 plus 0.5. Right, we can multiply this out, but for this, a third, or 0.3 times 25, that is 7.5. And then we have this 5/10 still. If you add that all together, that is equal to 8. So what that means, it takes 8 seconds to pass a book or squeeze a wrist with seconds with 25 students. Let's put students like that. All right, and the number, letter C. The actual mean time in seconds for a length of 25 students is 7.9 seconds. How does this compare to your prediction from the graph and the equation? It is very, very close. So we're going to say very close. All right, with the equation, we had 8 seconds. So we were just 0.1 seconds off. Right, so by that, I think a pretty good prediction. And then D, how is it making a prediction different from using a graph versus an equation? For the graph, or at least for interpolation, we just found the location on the line. Versus an equation, there's a lot there's a lot of computation. I wouldn't say a lot of computation, there was some computation, right? And arithmetic. All right, but that gives us an estimate, right? An estimate, while an equation gives you an exact value, right? Maybe when we're comparing on the graph, maybe we don't say it's 7.9, right? We probably estimate to 8. But let's go ahead and go to number 4. We're going to predict it for these other values for extrapolation. We're going to say just for 35 students. So y equal to 0.3 times 35 plus 0.5. Okay. So for this, you're welcome to use a calculator, but 0.3 times 35 is 10.5. And 10 and a half plus a half is 11 seconds. So 11 seconds for 35 students. Okay. All right, we're going to skip the other parts and then this last question, but we're going to go to this other context here with some specific values. All right. So this is a class conducted a similar experiment similar to the human chain experiment, but instead of holding wrists and squeezing it, each student held the shoulder of the student to his or her right, and the students recorded the time it took to squeeze around chains of different lengths. So we have, right, as you can see, 5 students all the way to 30 students, and it ranged in time from a little over a second to a little less than 7 seconds. First, let's draw a line of best fit. Right, I think a line of best fit somewhere like this. Well, actually, if I draw this is not a good line because everything is below this, everything is above. So somewhere in between, we're catching some of the points, but maybe not all. I think that is a good trend for our data set. Okay. Anyways, going to the next page, page 471. What is the explanatory variable and response variable in this situation? So the explanatory, or as always the x-axis, it is the chain of students. Or chain length, we'll just put students. And then the response variable, right, that is the mean time in seconds. Let's put time. And it says, analyze the scatter plot. Do the data appear to be close to a line? And if so, what is the association? Okay, I would say, yeah, the data is pretty close to the line, so it forms a linear relationship. With, and then what type of association? It's a positive slope, so we would say that that's a positive association. And I'll just abbreviate there. And then it says using a straight edge. We already did this. We already drew the line, but we will have to write the equation of that line. So define your variables and include the units. So with this, we're going to choose some of these points. Maybe I'll choose this point and this point here. That's not quite exactly on, but it's like close enough that I'll use it. So let's write the ordered pair here. And also the y-intercept is about half. Okay. So this we can say is going to the right. That's 8, comma, and going up, that's about, let's say 2.2. And then this point right here, that is about 20, and going up, that's about 4.5. Okay, so let's use both of those points to find the slope. Right, but in slope-intercept form, y equal to mx plus b, right, we know that the b is roughly 0.5. Okay, but let me rewrite it. 8, comma 2.2 and 20, comma 4.5. Okay. So for this, let's go ahead and figure out our slope. So y2 minus y1, this will be 4.5 minus 2.2, and this will be 20 minus 8. If you subtract that, you'll get 2.3 divided by 20 minus 8 is 12. I'm going to plug that into a calculator. All right, 2.3 divided by 12. That is 0.19. So that is very close to 0.2. Okay. So for this, that's the slope. So we'll put y equal to 0.2x plus 0.5. So that gives us the equation, and we'll do varying things to the equation. So with this, we have to figure out what is the slope. The slope, what does that mean? This means that it'll take, it represents the change in time to complete the change per student. So it's about 0.2 seconds, we'll say per additional student. Interpret the meaning of the y-intercept. The y-intercept was actually the same as the first one. So that is the actual time it will take for 0 students to complete the chain is about half a second. So 0 students to complete, this is where we begin, is half a second. Now, right, why does it take half a second? Right, this is just an estimate. It's very close to 0. It would most likely be 0 students, or sorry, 0 seconds. But let's use that to make a prediction for this next part. Okay. How close to the y value of, so this is the actual time it would take 0 students to complete a chain is 0 seconds. So, right, we'll say that the 0.5 is close to 0. And then now let's make a prediction. Use your equation to predict the mean time it will take to complete a chain of 20 students. So we'll plug that in here. Instead of 0.2x, 0.2 times 20 plus 0.5. Okay. So 0.2 times 20 is 4. And 4 plus a half is 4.5. So what that means, it would take 4.5 seconds for 20 students, right, to complete a chain of 20 students, to complete the chain. The chain. Okay. All right. And then moving on to continuing activity 2, we're going to use this, but predict for one more value of 35. So y equal to 0.2 times 35 plus a half. All right, this would be 0.2 times 35. You can use your calculator, but that's 7. And 7 plus a half is 7.5. Okay, so 7.5 seconds to complete a chain of 35 students. And then here, right, is it faster to complete a chain by squeezing wrist as the first one or squeezing shoulders? Since for squeezing wrist it was 0.3 seconds per student, and squeezing shoulders it was 0.2. That means squeezing shoulders, because right, that was squeezing shoulders is less time of 0.2 seconds. Right, and the y-intercept was the same for both of them. We're going to get to some practice, and this will be very similar to your assignment. So it says estimate the equation. Now this is going to be variable as long as you get something close. But I'm going to give us an example here. Right, this I think is probably a good line of best fit. This maybe not, because it's below a lot of it. This maybe not, because it's the points are below. The points are above. So somewhere close. But it's also got to intersect the y-axis, because that's got to be, right, we need the y-intercept in order for us to write the equation. So for this, the y-intercept is roughly, it's about 8.5. But let's figure out our slope. So the slope of this, we can use this point, and instead of using the slope formula, why don't I use just rise over run? So let me find a point that might be good. Maybe not one of these black points, but maybe I could choose like this point right here that I'm connecting. Let me find the slope from here to here, and then from here to here. Okay, the rise, we're going from 8.5, so it looks like we're going by half. So a half, 1, 1.5, 2, 2.5, 3, 3.5. Looks like that's 4. And then this is the y-axis, or x-axis is also going by half. So a half, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, 6, 6.5, 7, 7.5, 8. It's about 8.5 to the left, but that'll be negative. So if we divide our rise over run, put this into a calculator, it's going to be roughly a half because 4 is half of 8. All right, that is about 4.7 or 0.47. It'll be negative 0.47. So the equation, if we have this as the slope and this right here 8.5 as the y-intercept, the equation would be y equal to negative 0.47x plus 8.5. And you're more than welcome to use a calculator for this portion of it. Let's do one more. Which one should we do? I should say for this one, for 3, this one has no association because there is no line trend that's forming. You know what? Since we did those two, we'll say these other ones as U-dos, but that's the general idea of what you're doing here. We're skipping talk to talk. For the assignment, you're doing all of number 1. Number 1 all. And then on the back side, each portion of this is just like, this is just one problem, this is one problem. You're just figuring out which one's the better line. So we're going to say for all of number 2 as well. So number 1 and number 2. Okay. All right, let's get started. Let me know if we have any questions.